characterization. And I mentioned yesterday that my lab, the Seascape Ecology Mapping Lab, we tend to work further down the pipeline, looking at the integration of different data sets and generating those thematic maps. So we've fallen a little bit down the backscatter rabbit hole to try and really understand. Backscatter is such a good proxy for understanding the seafloor geology and biology. So we kind of straddle that biological, geological, oceanography field. So what I wanted to talk today is just to start off just spatial, the spatial context for ecological study of the ocean floor and the benefits that backscatter can offer. And that's really our key interest in backscatter. And then I just want to talk about some of the multispectral backscatter work we've been involved with. A recap, some of you may have seen the method-based stuff we've done with the early ultrasonic data sets. And then just expand a little bit more on the OI5 Become project, which I briefly introduced in my navel gazing presentation on the first day, and then just some ideas about future research. So what is benthic habitat mapping? Well, the definition that I like is from the 2011 review paper that I wrote, was the use of spatially continuous environmental data sets to represent and predict biological patterns on the seafloor. And we can interpret that in different ways. It can be gradational representations, or they can be hard boundaries that draw around different areas that represent different aspects of the seafloor in terms of its habitats, its geology, its biology. And what we've seen over the years, and this really coincides with multi-beams coming online. This is data that Ben's been pulling together for another review we're working on. But we've seen an incredible rise in the literature when you just use the term benthic habitat mapping. It's really taken off as a field of study. And what we've really seen is, well, you break that down by mapping systems that are used in those studies. So this is just the proportion per year and the numbers. We see multi-beam really taking off as it became more accessible. The early studies, a lot of single beam echosounders, using ground discrimination systems and side scan, they've tended to come down and multi-beam's gone up. So multi-beam has been a really great tool for understanding seafloor biology and benthic habitat. And I like to think of it as being equivalent to terrestrial landscape mapping. So I like the term benthoscape approach. Benthoscapes are the benthic component of the seascape. We're thinking about how we map the environment. On land, we use aerial or terrestrial remote sensing, and we can actually delineate into different landscape classes. And that's linked to the resolution of the sensors. On land, it's nice and easy. We can use optical methods to map everything accurately. We can ground truth just by going through with a handheld GPS and give a label, a landscape label to each of these: deciduous forest, urban habitat, pastoral, without any difficulty. And those maps are incredibly useful. So as an ecologist, if I want to study leaf litter in invertebrates, I know I need to go where there's leaf litter, and I go to this particular landscape class. Sounds really simple. But as oceanographers, we don't see the landscape, we often don't have the maps. So if I'm trying to sample those leaf litter invertebrates from a hot air balloon above the cloud cover and I don't have a map, I don't know where I'm sampling, what I'm collecting, or the spatial configuration of the landscape units. So this is where the multi-beam data, particularly backscatter, comes in. It helps provide that spatial context for the ecology. And we can really start then to understand the ecological processes, the spatial patterns of the ecosystem. We can use them for management, we can use them for science applications, we can use them for a whole range of different things. Hence our trip down the backscatter rabbit hole, because that's the proxy. And again, thinking about this as a slide that Jonathan Buvan put together for a joint presentation again on some of the multispectral work, but it's a great example. Terrestrial remote sensing, we can use different spectral bands, we can extract information from those combinations of spectral bands to map things like landscapes. So we tend to have good coverage and much more discrimination power with our optical remote sensing. But different land cover types will have unique spectral signatures we can classify that. And what we've seen in the literature is really a move from, or really a cross application of a lot of the techniques and methods that we've seen for terrestrial remote sensing to marine habitat mapping. And of course, thinking about the analogy, if you're measuring at different spectral bands, you can combine those and you can actually start to use that to understand spatial patterns. So this is where the backscatter is so important, and increased information from different frequencies in terms of the seafloor response. One thing to point out, the big difference between marine and terrestrial. In terrestrial, it tends to be the vegetation, so we're actually mapping the biology, which is the habitat component primarily, not always. In the marine realm, often it's the geology that we're mapping, which is that correlation with the backscatter. Again, not always, but sometimes you can directly image the biological components of the seabed, things like kelp, coral, those kinds of environments. So that takes us on to some of the early multispectral work. So this was collaborative work that we did with R2Sonic and QPS, dating back to 2016 when they launched their new multispectral system. So the 2026 time still does. It changes the frequency by ping. So in post-processing, you can unravel pings, you can unravel bathymetry by frequency as well. You can start to explore the differences. And we chose a site inside the Bedford Basin. We knew this was an interesting site in terms of the seafloor, pretty complex, but a good place just to test out and look at some of the differences between these frequency bands. This is what we see. The Bedford Basin, there's a sill, drops down to about 70 meters. And in the mouth of the Bedford Basin, just across the harbour from the Bedford Institute, you can see it's consistently high backscatter in all three of these frequencies. As we drop down into the basin, we have low backscatter on the higher frequency system. And then we start to see this really complex higher backscatter appear on the seafloor. And this has been described and documented. Gordon Fader, there's a 164-page document describing the geology of the Bedford Basin and the Halifax Harbour. So the Geological Survey of Canada studied this at length. This is an older side scan, 100 kilohertz track that is described. They've identified these features as dredge spoil. So it's Halifax environment for being built when the material was dumped into the Bedford Basin. But that's been overlaid and smothered with softer sediments over the years. So this is just a little GIF where it's cycling through the different frequencies. You can see these spots here are what we've assumed with a dredge spoil that's been overlaid with material. So we've extensively ground truthed this. We go out into the Bedford Basin a lot for training students. We've sampled it extensively. These are camera transects, and you can see this is the 400 kilohertz mosaic. Soft sediment is visible on all the camera drops in the deeper part of the basin. The bottom looks a lot like this. There's quite a lot of bioactivation, a lot of biology activity going on there. As we come in to the shallower areas, we get a mixture of mud overlaying some of that really hard ground, and then we get some pretty clean, hard substrate right in the mouth of the basin where the tides are carrying away a lot of those fines. So the 400 kilohertz corresponds better with our ground truthing. But to try and validate and understand exactly what these were, again, we went out and used different validation methods. So we took a multi-core and we targeted on and off some of these hard spots. So we started off with areas that are consistently low backscatter on our three frequencies. Of course, we got full penetration of our core, half a meter penetration into that soft, peaty mud at the bottom of the Bedford Basin. We got a little bit off onto an area that's starting to get a little bit higher backscatter on the lower frequency. We get a little bit more penetration. And right on top of those hard spots, we only get maybe a couple of centimeters, and physical graph samples also brings up some of that coarse gravelly material underneath. So we're pretty confident what's going on there. There's a frequency response. We're crunching through that mud layer with the low frequency. So in theory, we talked a lot about the theory, but to angular response curves. We can predict these things, but the seabed environment is never that simple. There's a lot of complexity, even in areas where we have homogeneous sediment. So this area was particularly complicated. So in theory, we can think about the different penetration depths of each of those frequencies, 8R, 45, and in the outer reefs. But that's very hard to unpack with a data set like the Bedford Basin because there's so many unknowns. And Ben's going to talk a little bit about this in his presentation and some of the work. So I'll leave it for him to expand. So this was really the impetus for the OFI Become project, where we wanted to try and simplify this. And let's go in the field and try and collect and really extensively ground truth areas that we don't have the complexity. So I introduced the OFI project today. This is the OFI Become project. Down here, work package 4.3, I lead on the multispectral. The work package, we're collaborating with external partners with this. So Jens, who's here, Alex Bastos, and Pedro Menandro, who were online. Freeney at the Doherty, plus a few other colleagues at Dalhousie. And the idea was to build on our earlier multispectral work, try and find some good field sites where we could do some empirical data collection. So the idea was to collect multispectral backscatter data sets under more controlled experimental conditions in suitable field sites, and then really extensively with high spatial accuracy we could ground truth that area and measure things like grain size, bottom roughness, geotechnical measurements of the sediment, really trying to get as much information as possible from these locations. And compare those CEQA measurements to our backscatter measurements across the range of insonification angles. Compare how those measurements vary over different substrate types. That's always the problem with reference sites we've heard a lot about. Finding good sites is always a challenge. And evaluate to what extent the angular range analysis and the backscatter signal over different operating frequencies can be used to help predict those CEQA properties. So this is the work of Ben Petrolio, who's a master's student. Unfortunately, Ben's on a leave of absence, otherwise he would be presenting this. And the project stalled a little bit because he's away at the moment. But essentially, he selected these sites through a lot of extensive investigation. We've got a mud site in Head Harbour in St. Martin's Bay, and a sandy site further out. And at each site, what we did was a broad scale data acquisition of a larger area, and then we selected a smaller, just 500 meter by 500 meter area that we really extensively ground truth, put down some ground lines and some subsurface marker buoys so we could actually see the buoys on the multi-beam data, and we could accurately georeference with divers where we were taking the course. And essentially, we went through and measured as many things as we could within the scope of the project and the resources that we had. So diver surveys, we collected push cores into the sediments. We know exactly where they are, we brought them back. We did sediment surface graph samples. We've been using a free-fall cone penetrometer to measure some of the properties of the sites as well. And then we've been using a drop camera system, which my group has developed in-house. One of the things we want to try and do here is measure some of those variables that are really hard to capture, like intermediate scale roughness. So this is the drop camera system. It's a 4K camera system. We throw it over the bottom, and we've been using Pix4D to generate high resolution point clouds. Great 2D video, so it's really great for visualizing the benthic environment. We can also extract the point clouds, and we're looking at ways that we can measure things like the intermediate roughness at the bottom, not at the grain size level, but at the next scale up, which might also be very useful for understanding some of those backscatter patterns that we're seeing. Even though we're pretty confident that we've got a fairly homogeneous sites at these locations, there is variability. We've got bioturbation, there's organisms digging in the mud, there's some bed forms on the sand side, so we feel that this could be really informative to help unpick some of those relationships. We haven't gone very far with the data analysis. This is really sitting waiting for Ben to return. So this is our growth scale area in Head Harbor. So Halifax is here. This is right at the top of St. Margaret's Bay. So we wanted to decide it was easy to get to. We mapped this broader area, and then our small site is right in the middle. We wanted a very homogeneous area with as little variability as possible. And our push doors show that we don't have any complications like we had at the Bedford Basin. There's no stratification, well, it's little stratification. We're in the process now of analyzing these cores to take as many measurements as we can. And we've got those from the study area. We've got multiple overlapping and sonification geometries. We've also unraveled backscatter by frequency, and we've generated surfaces for the broad area where we can see we do have some variability in the broader side. Side in the middle, we've got pretty homogeneous segments. We've been looking at the differences in terms of the bathymetric surface from each of those frequencies. I've found some really interesting results. So these are just very preliminary outputs that Ben worked up before he went on his leave. Backscatter across all these different operating frequencies over this smaller side in the middle, roughly the same. Probably about a 2 dB difference, and we need to do a little bit more work with the data. What was interesting was looking at the bathymetric surfaces generated from that mud location by frequency. See, really interesting trend across those operating frequencies by comparing the depths. Quite a nice response there in terms of penetration depth. We haven't gone very far, but we are looking at the angular response curves across those frequencies. And then also looking at depth penetration by the grazing angle. So we're trying to unpick as much as possible. Again, we can start to see some differences there by grazing angle in terms of penetration depth into the surface of the bottom. So these are things that we will explore much further in the future, and I think Ben will probably pick up on a few of these points during this presentation. Okay, so just to finish, just wanted to share some thoughts on future research. So addressing those questions, what is the current state of the art of multi-beam sonar research and development, and where are the research gaps? For us in the research that we do in my lab, particularly trying to understand ecosystems, multispectral really is an exciting development, just because we've got increased ability to understand differences in the seafloor, whether it's geological or biological or a combination of the two. And likewise, water column. We've got a lot of information there, particularly in that near seabed. Peter mentioned yesterday some of the work that he did with Deakin University. Biogenic structures that stick up above the bottom. We can extract a lot of value, I think, from looking at some of those. So improved environmental characterizations. New systems, engineering challenges, thinking about different geometries and different ways that we can collect the data. There's a lot of information packed up in there. Ben will touch on this a little bit, but we feel there's more information to squeeze out of the backscatter in terms of our understanding. Maybe there's new ideas that come about from the manufacturers and the technology providers in terms of increasing or changing that insonification geometry or the way that we do the surveys. Priority research areas that require attention. Well, I think the big one that keeps coming up is inter-system comparison and consistency. Same area should give us the same information from the different brands of sonar, whatever software package we use. That's a fundamental thing I think we need to solve as a community that we still have. Ben's going to show some ways of simple corrections that we do to harmonize things like backscatter for multi-source data. But if we can get it right in the first place, it'll solve a lot of that problem solving within the academic community or the downstream mappers. And then future role for the Backscatter working group. I think it's been such a success over the last 10 years plus. It's really progressed the field. It's helped the end users understand better. And I still think that facilitating collaboration, keeping the group going. I liked what Alex presented today in that vision. I think there's a lot of potential to spin out different sub-themes that we can address and really put some focused effort in. Multispectral being one of them. And I also think we should be pushing for accepted standards. I think that's something now that there's an appetite for it. And I don't know how we do that. It'll be interesting. Looking forward to the conversations later today to see how we can do it. All for me.